Let me ask you something that sounds so simple you might laugh. What keeps a train on the track? Go ahead. Think about it. I bet most of you just pictured those little lips on the wheels. The flanges, those raised edges that stick out on the inside. You figured the flanges bump against the rail whenever the train starts to wander, and that keeps the whole thing lined up, like bumper rails in a bowling alley. And I want you to hold that answer in your mind. Feel confident about it, because when I show you what actually happens, the look on your face is going to be worth every minute we spend together today. See, I used to ask this question in my classes. I would walk in and say, all right, here is a train, 2 steel rails. The wheels are sitting on those rails. The whole thing is moving at 60 miles per hour. What keeps the wheels on the track? And every hand that went up said flanges. Every single one. Smart students, graduate students, some of them, they all said flanges. And they were all wrong. Not completely wrong, but wrong in the way that matters. Wrong in the way where you think you understand something, and that feeling of understanding is actually blocking you from seeing the real thing. That is the most dangerous kind of wrong in physics, by the way. Not ignorance. Confident ignorance, the kind where you stop asking because you think you already know. I would see it in their eyes. That settled, comfortable look. Flanges. Done. Next problem, and I would say, are you sure? Are you really sure? And they would nod. Some of them would even look slightly annoyed, like I was wasting their time with a kindergarten question. That is exactly when I knew I had them, because the real answer is so much better than flanges. It is one of those answers that once you see it, you can never unsee it. It changes the way you look at every train, every wheel, every curved piece of track for the rest of your life. And it teaches you something about physics itself, about the way nature solves problems that goes far beyond trains. So let us start at the beginning, the real beginning. Let us look at a wheel. Take any wheel you want, a car wheel, a bicycle wheel, a wagon wheel. What shape is it? It is a cylinder, a flat cylinder. The part that touches the ground is straight across, or close to it. When you turn the steering wheel in a car, the front wheels angle left or right, and the whole thing follows. Simple enough. Now a train wheel is different, and I want you to pay very close attention to the difference, because this is where the whole story lives. A train wheel is not a flat cylinder. If you could slice it in half and look at the cross-section, you would see that the tread, the part that actually sits on the rail, is slightly sloped. It is wider on the inside near the flange and narrower on the outside. In other words, the running surface of the wheel is not flat. It is a cone, a very gentle, very shallow cone. The taper is not dramatic. You might not even notice it if you glanced at a wheel sitting in a rail yard. But it is there, and it changes everything. Before we talk about why that matters, let me give you the problem. The real problem, the one my students never thought about until I forced them to. Look under your car sometime. Between the 2 drive wheels there is a thing called a differential. A gorgeous piece of engineering. What it does is this: when you drive around a curve, the wheel on the outside of the curve has to travel a longer distance than the wheel on the inside. If both wheels were locked together, spinning at exactly the same rate, one of them would have to skid. The outside wheel would be dragged along too slowly, or the inside wheel would be dragged along too fast. Either way, you are scraping rubber against pavement and the car fights you. The differential solves this by letting the 2 wheels rotate at different speeds. It splits the engine's power between them in a clever way so that the outside wheel can spin a little faster and the inside wheel a little slower. Hundreds of gears inside a metal housing, also your car can make a turn without tearing itself apart. Beautiful, right? A real piece of work. Engineers spent decades perfecting the differential. It is a miniature marvel of mechanical ingenuity. You have bevel gears meshing with spider gears, all rotating inside a carrier, all bathed in oil, all machined to tolerances of a few thousandths of an inch. It is one of the most important inventions in the history of land transportation, and every automobile on Earth has one. Every truck, every bus. If you have 4 wheels and an engine, you have a differential. It is as fundamental to driving as the steering wheel. Now look at a train. A train has no differential. None. Zero. Nothing. Not one gear, not one bearing, not one clever mechanism to let the wheels turn at different speeds. The 2 wheels on each axle are pressed onto a solid steel shaft. One piece of metal, forged or machined as a single unit. When the left wheel turns, the right wheel turns at exactly the same angular velocity. Not approximately the same, exactly the same. They have no choice. Physics does not negotiate. So how does a thing like this go around a curve? Stop and really think about that for a second. Because this is the question that should bother you. This is the question that should keep you up at night. Every car in the world needs a differential to turn. Every truck needs one. These are vehicles that weigh a few thousand pounds. A locomotive weighs 200,000 pounds, sometimes more, and it goes around curves all day long without any differential at all. That should strike you as impossible, or at the very least deeply puzzling. And by the way, the problem is even worse than I made it sound. It is not just that the outside rail is longer. On most curves, the outside rail is also higher. It is tilted. The track is banked, just like a racetrack. Engineers call it super elevation. They raise the outer rail a few inches above the inner rail, so that the centrifugal force pushing the train outward is partially balanced by gravity pulling it inward and downward. This banking is important for comfort and safety, but it means the geometry is even more asymmetric than a simple curve would suggest. The outer wheel is higher, the inner wheel is lower, and the axle is tilted. Everything is off-center, and still the train navigates it smoothly. Think about that for a second. A train comes to a bend in the track. The outside rail is longer than the inside rail. That is just geometry. A bigger arc is always longer than a smaller arc. The outside rail has to cover more ground than the inside wheel. But both wheels are bolted to the same axle. They must rotate at the same angular velocity. They have no choice. If the wheels were flat cylinders, this would be impossible without slipping. The outside wheel would need to slide forward along the rail, grinding steel on steel, or the inside wheel would need to scrape backward. Either way, you would get shrieking, sparking, metal-on-metal friction at 60 miles per hour, pulling hundreds of tons. This should be a catastrophe. But trains go around curves every day, all around the world, smooth as butter. Millions of them, some of them weighing thousands of tons, some going over 100 miles per hour. So what is going on? This is where the cone comes in. Remember that gentle taper I told you about? The tread of the wheel is not flat. It slopes. The diameter of the wheel is slightly bigger on the flange side, the inside edge, and slightly smaller on the outer edge. Now watch what happens when the train drifts a little bit to one side. Let us say the whole axle shifts slightly to the right. The right wheel moves outward, so the rail contacts a part of the tread with a smaller diameter. Meanwhile, the left wheel moves inward, so the rail contacts a part of the tread with a larger diameter. Both wheels still spin at exactly the same rate, same axle, same rotation, but the left wheel is now effectively a bigger wheel, and the right wheel is now effectively a smaller wheel. What happens when you have a bigger wheel and a smaller wheel on the same axle spinning at the same speed? The bigger wheel covers more ground per rotation. The smaller wheel covers less. So the axle starts to curve. It curves to the right, the very direction it needs to go to get back toward the center of the track. This is not a subtle effect. You can calculate it. If the taper angle is such that the diameter changes by 1 millimeter over the width of the tread, then a lateral shift of just a few millimeters produces a measurable difference in rolling radius. And that difference, multiplied by the rotation rate, gives you a real steering force. Not a suggestion, not a gentle hint, an actual force that pulls the wheel set back towards center. The mathematics is almost embarrassingly simple. The circumference of a circle is pi times the diameter. Bigger diameter, bigger circumference, more distance covered per revolution. If the left wheel has a diameter that is even 2 millimeters larger than the right, then in one full revolution the left wheel covers about 6 millimeters more ground than the right. That does not sound like much, but a train wheel makes many revolutions per second. At 60 miles per hour, a typical wheel is rotating about 8 times every second. That means the left side is gaining nearly 50 millimeters per second on the right side. 50 millimeters per second of differential motion is a real curve. It adds up fast. And it does not stop there. If the axle overshoots and drifts a bit to the left, the exact same thing happens in reverse. The right wheel is now riding on a bigger diameter, the left on a smaller, and the axle curves back to the right. The train is steering itself. No gears, no mechanism, no computer, no driver input, just geometry. The shape of the wheel does all the work. I want you to appreciate how remarkable this is. An automobile needs a differential with dozens of precision gears to handle the speed difference between inner and outer wheels on a curve. A train handles it with a slope, a taper, a surface that is not flat. That is the entire mechanism. The solid axle, which looks like a problem, actually becomes part of the solution. because the axle forces both wheels to rotate at the same angular speed, and the coning converts that equal rotation into unequal linear speeds. The problem is the solution. Let me say that again because I think it is extraordinary. The shape of the wheel does all the work. A simple taper, a cone you would barely notice with the naked eye, gives the train a built-in correction system. Drift left, the geometry pushes you right. Drift right, the geometry pushes you left. The train snakes along the track in a gentle wave, always correcting, always coming back to center. And the flanges, those lips everyone thinks are doing the work, they almost never touch the rail. In normal running, on a straight track or a gentle curve, there is a gap between the flange and the rail. The flange is the emergency backup. It is the guardrail at the edge of a cliff. It is there for when something goes really wrong. If the lateral displacement gets too large, if the coning cannot correct fast enough, the flange catches the rail and forces the wheel back. But in normal operation, the flange is just sitting there, not touching anything. Most people have the whole picture backwards. They think the flanges are the primary system and the wheel shape is just some manufacturing detail. It is the exact opposite. The conical tread is the primary guidance system. The flange is the last resort. Now you might be saying, okay, fine, the cone helps the train steer on curves, but what does that have to do with staying on the track on a straight section? Excellent question. Here is the beautiful part. On a perfectly straight track, if the axle is sitting exactly in the center, both wheels have the same effective diameter. They cover the same ground per rotation. Everything is balanced. The train rolls straight. But tracks are never perfect. There is always a tiny bump, a slight imperfection, a gust of wind, a joint in the rail that gives the axle a nudge. The moment the axle shifts even a tiny amount to one side, the coning activates. One wheel gets effectively bigger, the other gets effectively smaller, and the axle starts to curve back. It overshoots, it passes through the center and goes a tiny bit the other way. The coning kicks in again in the opposite direction. The axle curves back. It overshoots again. What you get is a sinusoidal path, a smooth, gentle wave. The axle oscillates back and forth across the center line, never straying far, always correcting. This wavering path has a name. It was worked out mathematically by a German engineer named Klingel back in the 1880s. The wavelength of that oscillation depends on just two things: the distance between the wheels and the steepness of the cone. That is it. Two geometric parameters determine the entire guiding behavior of every standard gauge train on the planet. Now, I want to make sure you understand what I mean by wavelength here, because it is not the same as frequency. The wavelength is a distance. It is the distance along the track that the wheelset travels to complete one full side-to-side cycle. One sway to the left, one sway to the right, back to center. That is one wavelength. For a typical freight train wheel with a diameter of about 33 inches and a standard conicity, the Klingel wavelength is somewhere around 30 to 50 feet. That means for every 30 to 50 feet of track the train covers, the axle completes one full oscillation. At low speed, that oscillation might take a full second or two. At high speed, the oscillations come faster because you are covering those 30 to 50 feet in less time. And here is the key: the wavelength does not change with speed. It is purely geometric. Speed only affects the frequency, how many oscillations per second. The spatial pattern is fixed by the cone and the gauge. That is a beautiful result because it means the self-correction is always the same, whether the train is creeping along at 5 miles per hour or racing at 100. Think about that. Two numbers, the gauge of the track and the taper of the wheel. From those two numbers you get a self-correcting guidance system that works automatically at any speed, requires no moving parts, has no electronics, no feedback sensors, no actuators. It is one of the most elegant pieces of engineering in human history, and almost nobody knows about it. Let me push on this a little more because there is something here that connects to deep mathematics. The motion of the wheelset, this gentle oscillation back and forth, is what physicists call simple harmonic motion. It is the same kind of motion as a pendulum swinging, or a mass on a spring bouncing up and down, or a plucked guitar string vibrating. The restoring force, the force that pushes the wheelset back to center, is proportional to the displacement. Move a little, get pushed back a little. Move a lot, get pushed back a lot. That linear relationship between displacement and restoring force is the hallmark of harmonic oscillation, and it shows up in every corner of physics. When I first realized that a train on a track is a harmonic oscillator, it made me laugh. because a harmonic oscillator is the first thing you study in physics. It is the simplest system there is: mass, spring, motion, and here it is hidden inside a machine that weighs hundreds of tons and stretches half a mile long. The universe loves its simple systems. It keeps using them over and over, just dressed up in different costumes. Let me give you a picture that might make this even clearer. Take a paper cup, an ordinary disposable cup that is wider at the top and narrower at the bottom. Lay it on its side on a table. Give it a push. What does it do? It rolls in a circle. It does not go straight. It curves toward the narrow end. Why? Because the big end covers more distance per rotation than the small end. The big end is like the wheel riding on a larger diameter, and the small end is like the wheel riding on a smaller diameter. The cup naturally turns. Now take two paper cups and tape them together, bottom to bottom. You get a shape that is wide on both ends and narrow in the middle, like two cones joined at their tips, an hourglass shape. Put that double cup shape on two parallel rails, like pencils. Give it a nudge. It wobbles back and forth, but it stays on the rails. If it drifts to one side, the effective diameters change. It curves back, overshoots, curves back again. The same sinusoidal dance. That double cup shape is a rough model of a train wheel set. In fact, if you flip it around so the wide parts face inward and the narrow parts face outward, you have an even better model. That is actually what a train wheel looks like. The bigger diameter is toward the center of the track, and the smaller diameter is toward the outside. When the axle shifts, the inner wheel rises to a bigger part of the cone, and the outer wheel drops to a smaller part. Self-correction. You can try this at home. It takes about 2 minutes and a couple of cups, and you will see the physics with your own eyes. Use two pencils laid parallel as your rails, about 6 or 8 inches apart. Tape two cups bottom to bottom and lay them across the pencils so they can roll. Give them a nudge. Watch what happens. They wobble, they weave, but they stay on the pencils. Do the same thing with a flat cylinder like a soup can, and it will roll right off the edge. Here is something wonderful. This same principle was known to barrel makers centuries before anyone built a railroad. Traditional wooden barrels are fatter in the middle and narrower at the ends. That is the cooper's art. And one of the reasons for that shape, beyond holding the staves together, is that barrel-shaped containers can be rolled along wooden rails in a warehouse. Workers would lay 2 planks on the ground, set the barrels on their sides on the planks, and roll them from one end of the building to the other. Because the barrel is fatter in the middle, it self-steers. It weaves slightly, the same sinusoidal path, but it stays on the rails. You can see this in old photographs and films of breweries and shipping warehouses from the 1800s. Barrels rolling on wooden rails, wobbling gently, never falling off. The coopers did not know they were exploiting conic section geometry. They just knew that barrels with a belly stayed on the rails and straight ones did not. Practical knowledge arrived at through trial and error, centuries before anyone wrote down the physics. That is the way things often happen. The practice comes first, and the understanding comes later. The railroads used conical wheels for decades before Klingel wrote down the mathematics. The barrel rollers used bellied barrels for centuries before anyone thought about restoring forces in harmonic oscillation. Nature's principles are there whether you understand them or not. Understanding just lets you use them more deliberately. Alright, so here is where it gets more interesting. Because you might think, great, the cone fixes everything, trains are perfect, end of story. But nature is never that clean. There is always a catch. Remember that sinusoidal oscillation I described, the axle wavering gently back and forth? At low speeds, that oscillation is damped. The energy in the side-to-side motion gets eaten up by friction and the stiffness of the suspension. The wavering dies out. The train settles into a smooth ride. You barely feel anything. But as the speed increases, something changes. The inertial forces in that oscillation grow. The mass of the wheelset swinging side to side generates more and more lateral force with each cycle. At some speed, the energy being fed into the oscillation from the forward motion of the train matches the energy being dissipated by friction and damping. The oscillation stops dying out, it sustains itself. Go a little faster and the energy input exceeds the damping. The oscillation grows. Each swing is a little bigger than the last. The axle swings wider. The forces get stronger. The swing gets wider still. This is a positive feedback loop. The technical term is hunting. Hunting oscillation. The name is perfect actually. The wheel set is hunting for the center of the track, swinging back and forth, searching, overshooting, searching again, like a dog sniffing for a scent, running left, running right, unable to settle. That restless seeking is what the engineers saw when they first observed it, and the name stuck. The physics of hunting is remarkably similar to a phenomenon that destroyed aircraft in the early days of aviation. Engineers called it flutter. An airplane wing at a certain speed would begin to oscillate. The oscillation would feed on itself, growing larger with each cycle until the wing tore off. Flutter killed many pilots before engineers figured out how to suppress it. And the mathematics that describes flutter and the mathematics that describes hunting are nearly identical. Two coupled motions exchanging energy, feeding off the forward velocity, growing until something breaks. That is not a coincidence. It is the same physics, the same equations. Whether it is a wing in an airstream or a wheelset on a rail, the underlying structure is the same. Energy from forward motion gets converted into lateral oscillation, and if the damping cannot keep up, the amplitude grows without bound. You have probably felt this if you have ever been on an old train going fast. That rhythmic lateral rocking, that side-to-side lurch that makes you grab the armrest. That is hunting. The wheel set is oscillating with growing amplitude and the car is rocking with it. And here is where the flanges suddenly matter. When the oscillation gets big enough, the flange slams into the rail. Hard. There is a sudden jolt, a bang of steel on steel. The wheel rebounds. It swings the other way, and the opposite flange slams. The train lurches violently. Forces spike to enormous levels. The rail gets shoved sideways. The wheel gets battered. Bolts loosen. Components fatigue. If you have ever stood near a track when a heavy freight train passes at speed and heard that rhythmic banging, that ka-chunk, 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 you might have been hearing hunting. The flanges hammering the railheads over and over, dozens of times a second. This was a genuine mystery in the late 1800s. Trains were getting faster, and at a certain speed they would start shaking themselves to pieces. Rails were damaged, wheels were destroyed, cars derailed. Nobody quite understood why. The problem was first noticed around 1880, 1890, when train speeds began to push past 50 or 60 miles per hour regularly. Before that, trains were slow enough that hunting was either absent or so mild nobody cared. But as the railroads pushed for speed, pushed for schedule, pushed to connect cities faster, they hit this invisible wall. Above a certain velocity, things fell apart. Think about what was happening. The very feature that keeps the train on the track, the conning of the wheels, was also the thing that could tear it off the track at high speed. The same geometry that produces gentle self-correction at 30 miles per hour produces violent oscillation at 100. The restoring force and the destabilizing force come from the same source. This is not unusual in physics, by the way. Many systems that are beautifully stable in one regime become wildly unstable in another. A pendulum hanging straight down is perfectly stable. Flip it upside down and balance it on its tip, and it is wildly unstable. Same pendulum, same forces, different regime. Or think about a bicycle. At walking speed, a bicycle is almost impossible to keep upright. You wobble, you overcorrect, you fall over. At a brisk riding speed, it practically steers itself. You can ride with no hands, and it just goes. The physics that creates stability at one speed creates instability at another. The speed changes the balance between competing forces, and below a certain threshold, one force wins. Above it, the other force wins, and the transition can be sharp, almost sudden. The hunting problem plagued railroads for decades. The speed at which it appeared was called the critical speed, and for much of the early 20th century it put a hard ceiling on how fast trains could go. The solution, when it came, involved the suspension. Engineers figured out that if you could add damping, if you could put shock absorbers and carefully tuned springs between the axle and the car body, you could absorb the energy of the oscillation before it built up. You could push the critical speed higher, and that is exactly what happened. The bogies, those truck assemblies that carry the wheels, got more and more sophisticated. They added yaw dampers, devices that resist the axle trying to rotate sideways. They added lateral dampers, springs with specific stiffness values. They tuned the entire suspension to eat up the hunting energy at higher and higher speeds. This is how the Japanese Shinkansen could run at over 130 miles per hour in the 1960s. And how modern high-speed trains push past 200 miles per hour today. Not by changing the fundamental wheel geometry. The cone is still there. The solid axle is still there. What changed is the suspension around them. The self-correcting cone does the guiding, and the suspension keeps the oscillation from getting out of hand. The Japanese engineers, when they were designing the Shinkansen in the late 1950s and early 1960s, made a deliberate choice. They reduced the conicity of the wheels, made the taper shallower. Less taper means weaker self-correction, but it also means a higher critical speed. The oscillation takes longer to build up. That trade-off, weaker guidance for higher speed, only works if the track is extremely straight and well maintained. And the Japanese built their high-speed track to extraordinary precision. Curves were banked exactly right, rails were welded into continuous ribbons, no joints, no gaps. The track was so smooth that the gentle conning, even with its reduced taper, was more than enough. The Europeans took a different approach. The French TGV, when it came along in the 1970s, used a more conventional wheel profile, but invested heavily in bogie design. Their bogies had sophisticated yaw dampers, carefully tuned lateral springs, and innovative articulation between cars. They treated the hunting problem as a damping problem and attacked it with damping solutions. Both approaches worked, both pushed speeds well past 150 miles per hour, and both relied on the same underlying physics. The cone, the solid axle, the Klingel oscillation. They just managed it differently. There is a third approach that some systems use, and it is interesting because it throws away the cone entirely. Some modern metro systems, like the Bay Area Rapid Transit System in San Francisco, use cylindrical wheels, flat treads, no taper at all. These systems rely entirely on the flanges for guidance. And you know what happens? They screech loudly. Every time they go around a curve, the wheels slip and slide, steel grinding on steel, because there is no conning to let the inner and outer wheels naturally adjust. The noise is extraordinary. Riders plug their ears. The system has spent millions trying to reduce it, all because they gave up the cone. That screech is the sound of a problem that a simple taper would solve. It is layers of engineering built on top of a single geometric idea. Now let me pull back and show you something even deeper, because this is the part that really gets me. The conical wheelset is a self-regulating system. It detects a problem and corrects it automatically, using nothing but its own shape and the laws of physics. There is no central controller, no brain, no sensor. The intelligence, if you want to call it that, is embedded in the geometry itself, and this pattern shows up everywhere in nature. Your inner ear uses the same principle. There are tiny, fluid-filled canals in your skull, semicircular canals, and when your head tilts, the fluid shifts. That shift triggers nerve signals that adjust your balance muscles. Tilt detection, automatic correction, stable equilibrium. No conscious thought required. A river does the same thing. If water flows faster on one side than the other, the fast side erodes the bank, the slow side deposits sediment, and the channel shifts. The flow adjusts. The river is constantly correcting its own course. If it drifts too far, it meanders. Those beautiful S-curves you see in rivers from an airplane, those are the river's version of the Klingel oscillation. Overshoot, correct, overshoot, correct. The physics is different in detail, but the structure is the same. Displacement produces a force that opposes the displacement. Even at the atomic level, you see this: an atom in a crystal lattice sitting in its equilibrium position gets bumped. It feels a restoring force from its neighbors. It oscillates, just like the train axle, back and forth around the equilibrium point. And if it oscillates too hard, if you heat the crystal enough, the oscillation breaks free of the restoring force and the crystal melts. Stability to instability, the same transition, the same critical threshold. A thermostat in your house does it too. Room gets cold, heater turns on. Room gets hot, heater turns off. Oscillation around a set point. Overshoot, correct, overshoot, correct. The thermostat is a self-regulating system, just like the cone on a train wheel. The difference is that the thermostat uses a sensor, a switch, and a furnace. The train wheel uses nothing but its own shape. That is what makes the train wheel so remarkable. The feedback loop is built into the geometry itself. Remember, there is no separate sensor, there is no separate actuator. The wheel is the sensor and the actuator at the same time. In control theory, this is called passive stability. You do not need to measure anything. You do not need to compute anything. You do not need to apply any correction. The system corrects itself inherently by virtue of its physical structure. Active stability is when you measure, compute, and correct. Passive stability is when the shape of the thing does it all for you. Active stability is powerful. It lets you stabilize systems that could never be stabilized passively. But it requires energy, sensors, computers, and maintenance. Passive stability requires nothing. It just works. As long as the geometry is right, it works. The conical wheel is not just a clever trick for trains. It is an example of one of the deepest patterns in all of physics, systems that create order through geometry, without any external control. Let me go back to the wheel for a moment, because there is one more piece that most people miss. We talked about curves. We talked about the coning, allowing different effective diameters to handle different path lengths. But how much coning do you actually need? Here is the thing. If the cone is too steep, the self-correction is very strong. The axle snaps back to center aggressively. That sounds good, right? Stronger correction, better stability. But remember hunting. A steeper cone means a more powerful oscillation. The critical speed drops. The train starts hunting at a lower speed. So you have traded high-speed stability for low-speed stability. If the cone is too shallow, the correction is weak. The train wanders lazily, takes a long time to recenter, and the flanges end up doing more work. The flanges bang against the rails more often. You get more wear, more noise, more damage. So there is an optimum, a sweet spot, a cone angle that gives you strong enough correction to stay centered, but gentle enough that hunting does not kick in until you are going very fast. Finding that sweet spot was one of the great engineering challenges of the railroad era. Different railroads tried different profiles, different taper angles, different wheel diameters, different flange shapes. The standard that most of the world eventually settled on uses a taper of about 1 in 20. That means for every 20 units you move along the tread, the diameter changes by 1 unit. Very gentle, so gentle you might not notice it by eye. But it works. It works at 10 miles per hour, and it works at 100. It works on sharp mountain curves and long prairie straightaways. It works in snow and rain and desert heat. One geometric ratio, and the whole system balances. In practice, though, the wheel profile is not a perfect cone. If it were a perfect cone, the contact geometry would be too simple, too unforgiving. Real wheel profiles are slightly curved. The taper varies across the width of the tread. Near the center, where the wheel normally sits, the taper is gentle. Toward the flange, it gets steeper. This means that small displacements produce a mild correction, while larger displacements produce a stronger one. The correction force is not constant. It ramps up the further the wheel drifts. This is like having a soft spring for small bumps and a stiff spring for big bumps. It is a progressive restoring force. Small perturbations get handled gently. Large perturbations get handled aggressively. Engineers spent decades perfecting these profiles. They tested dozens of shapes, measured millions of miles of wheel wear, and gradually converged on profiles that give the best balance of stability, ride quality, and resistance to hunting. The Europeans and the Americans ended up with slightly different standard profiles. The American standard, called the AAR-1B, has a different tread shape than the European standard, the S1002. Each is optimized for its own track conditions, speeds, and loads. But both rely on the same principle. Both are gentle cones with carefully shaped transitions near the flange. Now, there is something else going on that I have not mentioned yet, and it is important. We have been talking about the ideal case. Perfectly conical wheels, perfectly straight rails, perfectly rigid axles. In the real world, the wheels wear down. Every mile of track grinds away a little bit of the steel tread. Over time, the profile changes. The cone becomes less cone-shaped. The effective taper shifts. And when that happens, the self-correction weakens or changes character. This is why railroads have wheel-truing lathes, enormous machines that recut the wheel profile back to the correct shape. It is a constant battle. The geometry that keeps the train safe slowly erodes under the very forces it was designed to manage. And the rail wears too. The contact patch, that tiny area where wheel meets rail, is only about the size of a small coin. Think about that for a moment. A freight car might weigh 80,000 pounds. All of that weight is carried on 8 wheels, 10,000 pounds per wheel. And that 10,000 pounds presses down through a contact area the size of a dime. The pressure at that contact point is staggering. We are talking about pressures that would crush most materials. Steel can handle it, but just barely, and not forever. Through that little patch, all the forces of guidance flow. The lateral forces from coning, the longitudinal forces from braking and acceleration, the vertical forces from weight, all through a spot the size of a coin. Over millions of wheel passes, the railhead changes shape. It develops a groove, a dip, a profile that no longer matches the design contact geometry. The wheel and the rail are in a constant conversation. The wheel presses on the rail pushes back. The contact patch deforms slightly, both the wheel and the rail. There is a thin zone where the steel is actually being elastically squished, like pressing your thumb into a rubber ball, except the deformation is measured in thousandths of an inch. In that tiny deformed zone, the forces of adhesion live, the creep forces as engineers call them. Not gross sliding, not slipping, but a subtle elastic deformation that transmits lateral and longitudinal forces without any actual skidding. It is through these creep forces that the conning does its work. The geometry says this wheel should curve this way, and the creep forces at the contact patch deliver the actual force that makes it happen. Without adhesion, without that elastic grip between wheel and rail, the conning would be useless. The wheel would just slide sideways instead of steering. So the railroad has to grind the rails too. Special trains with grinding stones ride the tracks at night, shaving the railhead back into spec. These are enormous machines, some of them carrying 40 or 60 grinding stones, each one spinning against the rail at high speed, sculpting the rail profile back to its designed shape. It is an invisible industry. Most people have never heard of rail grinding. But it is one of the most critical maintenance operations in all of rail transport because it preserves the geometry that makes the whole system work. And it is not just about shape. As the rail wears, the effective conicity changes. If the rail develops a hollow groove, the contact point shifts and the equivalent taper might increase or decrease unpredictably. An increase in effective conicity lowers the critical speed for hunting. That means a rail that was perfectly safe for trains at 100 miles per hour might, after enough wear, start causing hunting at 80. The maintenance does not just keep things pretty, it keeps them safe. It keeps them safe. Here is what I find wonderful about all of this. The answer to what keeps a train on the track is not a thing. It is not a device or a mechanism or a bolt or a brake. It is a shape, a geometric idea, a cone. And that cone has to be maintained, recut, reground, watched, measured, and cared for every day all over the world, on every rail line, on every wheel of every train. The next time you are near a railroad crossing and you hear that rhythmic clickety-clack as a freight train rolls by, listen carefully. That sound is the axles passing over joints in the rail, but between those clicks, the silence, that smooth, steady glide, that is the cone doing its work. The wheels are waltzing, shifting side to side in a smooth oscillation you cannot see and cannot hear, guiding 100 tons of steel around gentle curves with nothing but the slope of a surface. Let me tell you one more thing, and this is the part I love the most. When I would explain this to my students, when I would draw the picture and show the geometry and work through the logic, something would happen. They would get quiet because they realized they had looked at a train wheel 100 times and never noticed the taper. They had ridden trains and never wondered how a solid axle goes around a bend. They had an answer, flanges, and the answer was so satisfying that they never asked the real question. And I would tell them that is the whole game. That is what physics is. It is looking at the things you think you understand and asking, do you really? It is noticing the gap between the story you tell yourself and the story nature actually tells. Because nature's story is always better. It is always more elegant, more surprising, more beautiful than the one we made up. A cone. The answer to one of the most basic questions about one of the most important machines humans ever built is a cone. Not a computer, not a gyroscope, not some elaborate feedback system. A cone doing what cones do, because the geometry of a cone makes it inevitable. You could have figured this out yourself. All you needed was to look at a wheel cross-section, tilt your head and ask, why is it shaped like that? Why not make it flat? And there you go. You would have uncovered one of the cleverest self-correcting systems in the history of engineering, and you would have done it just by paying attention. That, I think, is the deepest lesson here. Not the coning of wheels, not the hunting oscillation, not the Klingel wavelength or the critical speed or any of the technical details. The lesson is simpler than that. The lesson is never trust an easy answer, especially when the easy answer makes you stop asking questions. The flanges feel like an answer. They look like an answer. They look like an answer. They are right there, visible, obvious, sticking out like little shelves on every train wheel you have ever seen. Of course they keep the train on the track. What else could they be for? And that obviousness, that feeling of, well, duh, is exactly what stopped nearly everyone from finding the real one. Physics is full of these traps. People thought heavier objects fall faster because, well, obviously they do. Drop a rock and a feather and see for yourself. Except they were wrong. People thought the Earth must be standing still because, well, obviously we would feel it moving. Except they were wrong. The obvious answer is the most seductive lie in all of science. In physics, and honestly in everything else too, the moment you feel satisfied with your understanding is the exact moment you should push harder. Scratch the surface. Look at the thing one more time. Because underneath the easy answer, there is almost always a deeper one. And the deeper one is almost always more elegant. A train wheel is a cone. That cone keeps 100 tons of steel on 2 narrow strips of metal at 100 miles per hour, around curves in wind, in rain, over mountains, across continents. It does it silently, constantly, without ever being asked, and nobody notices. Well, almost nobody. Now you know, and the next time you see a train, you will not think about the flanges. You will think about the cone. You will think about that gentle taper, that invisible slope, doing its quiet work. And I think you might smile, because you will know something that almost nobody around you knows. You will understand a piece of the world that was hiding in plain sight. That is what physics gives you. Not just facts, not just formulas. It gives you eyes, better eyes than the ones you were born with. All right, I want to leave you with a question. We talked about how the conical wheel creates a self-correcting oscillation on a straight track, and how it lets the wheels handle curves even though they are locked to a solid axle. But here's what I want you to think about. What happens if you run the train backwards on the track? Same wheels, same cone, same axle. Does the self-correction still work, or does the geometry do something different when the taper is facing the other way relative to the direction of travel? Think about it. Argue with yourself. Draw a picture. And when you figure it out, tell someone. Because the best part of understanding something is sharing it with someone who does not understand it yet.